Okay, okay, welcome to lab here. Give everybody just a second to get in, then we'll kind of continue on what we were doing. Okay, like I said, I'm going to kind of continue reviewing just for a little bit here. Let me get into the next chapter as well, and then we'll stop. And again, not much scheduled, obviously, for lab period this week, except for the exam and the final this week. So the 2 other days, sort of chance for you to maybe study a little bit. Obviously, if you have questions, you could ask and stuff like that. You could chat me some questions a little bit later on and stuff like that. A couple of things before we get started, just to remind, let's see, exam tomorrow will be sort of the same format. So again, you'll be into the Zoom meeting. And again, it should cover, like we talked about in lecture, our complex ion from chapter 16 or KFs, our all complex ion transition metals, all that stuff from 21, and then all of kinetics as well, which we pretty much finished last time. Just kind of touched up on a little bit of stuff here. Also, homework will be due, right? So make sure you get that stuff done this week as well. In terms of a quiz, I did post a quiz. It's sort of a review type quiz, so it covers some questions from some different chapters and stuff like that. Since I realized we didn't really take any quizzes, so probably good to give you something, I suppose. So should hopefully be some easy points, I would hope. It'd also be some nice review of some type of the questions that we've sort of covered throughout the semester as well. So that is due, I believe, on Thursday, and it's up there on Canvas. I think it should be the very top of Canvas where you can find that if you need. Also a link through the announcement that was sent out about it a couple days ago. So again, that should hopefully be a nice little review maybe. Won't obviously cover everything, but also should be hopefully some easy points, I would imagine, as well. So don't forget to turn that in, because that is worth points, and it does count, obviously, towards points and stuff like that. So make sure that you do get that one in as well. Other than that, like I said, we're just going to do a little bit more sort of official reviewing here, since we just started chapter 13. And afterwards, like I said, the rest of the time, again, kind of open study and that type of stuff. You do have to officially still be here, yes. So, do whatever you need to do there, but you could study afterwards, obviously, and you got a lot to study. Exam tomorrow, and obviously final on Thursday, which will cover everything as well. Let's see, I think that's pretty much it, I think. All right, so we got to hear Le Chatelier's principle there in lecture. And again, just to touch on some of the highlight points of Le Chatelier's principle, as we talked about, really we're talking about a system that has reached equilibrium. So again, that rate of the forward reaction will equal the reverse reaction, and then something happens to it to really sort of mess up the equilibrium. And when we talk about stresses, that could be concentration. Let's see here, concentration. We could either add or remove. We can talk about pressure and volume. So that's another thing that we could kind of change and affect as well. In addition, temperature. And also a catalyst we talked a little bit about. So these are things that can be added to a system that's at equilibrium, and in certain cases may have an effect on it, may not have an effect on it, depending on sort of the situation. So we'll start with concentration first off. When we add concentration, it does shift away. So when we talk about AA is a good way to remember that. If you add, it shifts away. So what that means is if you add a reactant, we would expect the reaction to head towards the product side, away from the side where you added it. And if you add some more product, we would expect it to shift to the left-hand side, away from the product side where we added it. Opposite is true if we remove concentration. We expect it to shift towards the side that was removed. So if you remove a reactant, it should shift the equilibrium towards the reactant side, the side where it was removed. If you remove a product, it should shift it towards this product side, again, as it's removed. So we talked about sort of ways you could do this. Obviously, adding is pretty simple. You grab the bottle and you dump it in there, right? So that's pretty simple. Removing, right? Really, there's two sort of ways that we typically can remove something from a system that's at equilibrium. The most common way is to form some type of precipitate. And when we form some type of precipitate, that usually implies adding something that will react with something that's in the equation to begin with. So something that's there in that reaction to begin with will react with whatever you're adding. And the result of that is a solid would form, and you'll get this solid precipitated form. So why is solid important in terms of removing? Because if you remember, when we talk about equilibrium and K, right, in equilibrium, there's really two things that are not included in the equilibrium expression, right? And that are things that are solid, and that's things that are liquids. So those are two things that really don't have an effect on the equilibrium. And obviously, if we make a precipitate, that's essentially removing that guy out. And obviously, the precipitate that's being made will not have an effect on the equilibrium other than removing a reactant or a product. The other more common way that as well that you can sort of remove something from a solution really deals with hydroxide OH minus or H plus. And again, the formation of water is another very common way that you can remove something from a solution. Is something visually that you might not be able to sort of visually see occur, like a precipitate, that you can actually see the solid being made. But make the formation of water, especially where you have either hydroxide involved, right? That does not look like hydroxide. Made an N there, OH minus H plus. So if you have OH minus in the equation, or you have H plus in the equation, and pretty much you add either an acid or base to it, you will form water because H plus and OH minus makes water. Water is a pure liquid, so that's a very common way that we remove something like hydroxide or H plus from a reaction, is by that formation of water. So those are two very common ways that we could sort of do that. But again, when we add, it goes away from the side we added it to. Remove. When we remove, it goes towards the side we removed it from. Now, other things that affect equilibrium is pressure and volume. So if we increase the pressure, relationship to that is the volume would decrease, and vice versa. If we decrease the pressure, the relationship, sort of Boyle's relationship there, is that the volume would increase. And obviously in this case, when we're talking about pressure, we're really thinking about gases here, and you want to look at the equation and really deal with only things with G's next to them. And again, as we talked about, sort of the easiest way to sort of think about it is in terms of volume. So if we have a small volume in that area there, we would need less gas molecules, and that would alleviate the pressure. So if nothing occurs and we drop the volume, the pressure should start to rise. That's sort of the change that's going to occur. So to bring it back down, we need to go to the side that has less gas molecules, and that is obviously dependent on the reaction. Now, opposite is true if we sort of lower the pressure or vice versa, increase the volume. That means everybody has a lot more room to fly around. And because they have a lot more room to fly around, the pressure will start to come down. And because the pressure starts to come down, we need to actually shift to the side with more gas molecules. That should bring the pressure sort of back up to reach equilibrium. So this would shift to the side with more gas molecules. And that also is obviously reaction dependent as to which side has more or less gas molecules. This is also a situation, if you remember with Le Chatelier's principle, that you can get a sort of no change occur. And this is a place where you could have a tie. And what I mean by that is when you look on the reactant side, you have, say, 2 gas molecules. You look on the product side, you also have 2 gas molecules. So there is no side that's more or less gas molecules. So again, this is a place where potentially you could have a kind of no change situation occurring. Now, when we talk about some other things that affect it, temperature is another big factor in terms of affecting it. So when we talk about temperature, it's either going to be exothermic or endothermic. And exothermic means that heat and energy is released. And when we look at a reaction that is exothermic, that means heat and energy is considered a product, and it's on the product side. And it means that delta H value typically is a negative number. And that is different than if it's a endothermic process. Heat and energy is absorbed. Delta H there is usually a positive number. And because it's being absorbed, it is thought of as a reactant. And when we look at a reaction like this, exothermic or endothermic, again, it works really like in terms of temperature. Oh, little earthquake, hang on. I don't know if you felt it where you were. All right, so temperature. Either that or something hit the house. I'm not sure. We'll see. So the temperature works the same way as concentration. And which means if we increase the temperature, it will shift away. And if we decrease the temperature, it will shift towards. And so really on this one, you do need to determine whether or not it's exothermic or endothermic, and that's what's going to help you determine sort of which way is going to shift. And basically, if it is exothermic, that means that if it increases the temperature, it will shift away from it. So it would shift to the left. So if we increase the temperature, it should shift to the left. And if we decrease the temperature, that would be like removing it. So it should shift to the right. And vice versa would happen if this was endothermic. If we decrease the temperature, it would be removing it, and it would shift to the left. And if we increase the temperature, it would shift to the right in that particular case. Any questions on temperature there? So we talked about a couple of things as well that really will have sort of no change. So a catalyst, like we talked about today, is something that will speed up a chemical reaction. Again, as we talked about today, not going to be used up. in the reaction, but they're really a lot of times just to facilitate it occurring faster. And in that particular case, it will really have no effect on the equilibrium. It will not shift it to the left. It will not shift it to the right. So this is one where we would get no change occur. Other things that will sort of cause no change, again, are you could add something, for example, like a noble gas, which are chemically inert. So those will not have an effect on equilibrium. And as I mentioned before, sort of in that gas situation, you could end up with two of the same amount of gas molecules on the reactant side and product side, which means, again, there's no sort of larger amount or smaller amount. Any questions on Le Chatelier's principle there? Okay, so that should wrap chapter 13 stuff. So then we went into chapter 14. And chapter 14 was our acid and base chapter. And we talked obviously about acid and bases in there. The basic sort of definition, right, of our acid is something that can produce H plus ions in solution. Remember that in acid-base chemistry, H plus and H3O plus are equivalent to each other. So that's the hydronium ion, and that is the hydrogen ion. And really the difference is when you write the sort of formulas or the equations as to whether or not you get H plus or H3O plus, a lot of times with acids involve whether or not you include the water in the reaction. So we talked about something like hydrochloric acid, which is a strong acid, will 100% break apart into H plus and Cl minus. And if we don't write the water in the equation here, which is perfectly fine to do, like we talked about, here you can see we do get H plus. Now, it is perfectly fine as well to write the HCl plus the water. And in this reaction, this is where we will produce H3O plus and Cl minus. So these are, again, as we talked about, two equivalent reactions. Really the main difference here is we included water in the second one as opposed to the first one, and we did produce our H3O plus versus our H plus, but they are equivalent to each other. You could do it either way. Again, most people oftentimes will just do it this way, but again, this way, not wrong and also done a lot of times. So that's sort of, again, that difference between why in certain cases you get H plus and in other cases you get that H3O plus like we talked about, is whether or not you really sort of include the water there in that reaction. Now, a base, on the other hand, right, that sort of basic definition of a base is something that produces hydroxide ions in solution. And we associate hydroxide with bases, and a lot of strong bases, as we talked about, actually do have, right, the hydroxide actually in them. And when it breaks apart into a sodium ion and a hydroxide ion. And in this particular case, again, the production here of hydroxide means it obviously is a strong base. A lot of bases, especially strong bases, come from group 1 or group 2 on the periodic table like we talked about. Again, that's why they're called the alkali metals and alkaline earth metals, because alkaline means basic, right? So a lot of things like sodium hydroxide, potassium hydroxide, calcium hydroxide, you know, strontium hydroxide, all those guys, again, they actually have the hydroxide OH in it and makes them relatively strong. And again, a lot of them come from that first two groups on the periodic table where a lot of our bases basically develop from. Now, a more sort of generic definition of acid and bases are the ones that we talked about. And that was, for example, our Bronsted acid and our Bronsted-Lowry acid base. I guess I should not throw that guy out there. So our Bronsted-Lowry acid base. And a Bronsted-Lowry acid is a proton, right, donor. while our Bronsted-Lowry base is a proton acceptor. So this sort of definition of acid and bases, really the most sort of common definition of acid and bases that we come across. And the relationship here is we look at it in terms of either accepting a proton or an H plus or donating an H plus. Again, here the H plus is called a proton because it has one proton, one electron, and no neutrons. So when it loses that electron, it becomes a proton. The sort of consequence of this is we do gain acid and conjugate base pairs. So if we look at sort of that acid dissociation, where we do include the water, again here, this is our acid, so he's donating the H plus over. Going to make our H3O plus and our Cl minus. And again, there are two things that are related to each other. This guy and this guy are related to each other. This is our acid over here. Its partner on the other side, as we talked about, is conjugate base. Now, on this side, since the water is accepting the H plus, that means that the water here is acting as our base, and its partner on the other side is the conjugate acid. And the importance of that is the only difference that there can be, as we talked about, between these two things is just one H plus. So this guy has one less H plus going this way. This guy has one more H plus going the other way. So that again can be the only difference that's there, and to become a conjugate acid-base pair. Remember that although things may look similar to each other, they may not be acid-base pairs. So for example, H2SO4 and SO4 2 minus. These guys here are not pairs. The difference here again is more than one H plus. And this results from, we can see this by what we talked about, that essentially this guy will lose one H plus at a time. And that is why when we think about acid conjugate base pairs in this particular case, this guy here, our sulfuric acid and our hydrogen sulfate, they are pairs. These two guys are pairs. Again, the only difference is one H plus. As we go from that hydrogen sulfate to the sulfate, also going to be pairs. Only difference is one H plus. But again, if we try to jump from here to here, that is going to be our 2H plus difference, which again would not make them conjugate acid base pairs. Any questions on that there? Also good to understand the relationship, as we talked about here, that when we talk about just acid and bases, again, they are found on the reactant side. On the product side is where you find your conjugate acids and your conjugate bases. So if you're asked to give the conjugate acid for something, again, what you want to think about is, say you want to give the conjugate acid for this guy, you want to kind of think about it backwards. So if I want to give the conjugate acid, which would be this, its partner on the other side originally was a base. And the definition of a base is something that will accept an H plus. So that tells me that I should put the H plus on and get H2SO4 would be my answer in this particular case. So again, sometimes people run into a problem of, I know I'm supposed to just put an H plus on there or take an H plus off, but they're not really sure sort of, you know, should I put it on or take it off? So sometimes it's really good to sort of think about it one step back and decide, oh, okay, so what I'm looking at is an acid, which means by definition I should get rid of an H plus, or what I'm looking at, like in this case, was a base, so I should accept an H plus. So again, that's a really good way to sort of think about how to kind of go backwards, if you will, if you're just asked to give a conjugate acid or a conjugate base. Now, as we were talking about sort of this acid and bases, we talked about the idea of figuring out whether or not a solution was acidic or basic. And one way that we could do that is using Kw, which is the equilibrium constant for water. That is the H plus concentration times the OH minus concentration equals 1 times 10 to the minus 14. And again, we could use this to figure out whether or not something is acidic, basic, or neutral, the solution. And that is when the H plus concentration is larger than the OH minus concentration, then the solution would be acidic. If the H plus concentration equals the OH minus concentration, that means they both will equal 1 times 10 to the minus 7, which means it will be neutral in that case. And if the H plus concentration is less than the OH minus concentration, then that would mean that it is going to be basic. So we could do this to sort of generically calculate the H plus concentration, the OH minus concentration. It really is the same calculation regardless of which one you're doing. You're going to take Kw divided by OH minus. You're going to take OH minus is Kw divided by H plus. So really they're both the same. As we talked about many times when we got here to this sort of chapter, you definitely want to make sure that you are using your exponent button. Otherwise, you will find yourself off, especially when you're using logs and stuff like that. The relationship between OH minus and H plus is as one goes up, the other goes down. So as the H plus concentration increases, the OH minus concentration decreases, and vice versa. H plus goes down, OH minus will go up in that particular case. So again, this is one way that you could do it. In a lot of problems, you are sort of generically given the H plus concentration or OH minus concentration. But remember that if this was a strong acid or strong base, you could figure out the concentration from it by just simply looking at the concentration. So if this was 0.25 molar HCl, we know that this is a strong acid, which 100% breaks apart into H plus and Cl minus. It is a 1-to-1 relationship between these two things, which means the concentration of H plus is 0.25. It's also a 1-to-1 relationship between that and the Cl minus, which means again here the Cl minus would be 0.25 as well. And this would be good for something, you know, in terms of for trying to figure out the H plus concentration. You could also do that for OH minus, kind of works the same way. This also works really well for when we talk about sort of the pH scale, which we also talked about. The pH scale, which runs from 0 to 7 to 14. Below 7 to 0 is acidic. Above 7 to 14 is basic. And dead on 7 is neutral. And as we talked about, technically speaking, dead on 7 is neutral because that's the point where the H plus concentration, the OH minus concentration equal each other, and they both equal 1 times 10 to the minus 7, which if you calculate the pH, which we'll talk about here in just a second, would give you a pH of 7. And to do that, when we look at the scale, as you head towards 0, it becomes more acidic. And as you head towards 14, more basic. To calculate the pH, it is minus the log of the H plus concentration. And again, that will allow you to calculate the pH. There is a similar scale that we talked to, which is actually POH, and POH actually runs the same way, 0 to 7 to 14. It's opposite in the sense of if you're less than 7, it's basic. If you're more than 7, it's acidic. And this is why most people don't really think about the POH scale like we talked about, because in everybody's head, they usually have the pH scale kind of in their head. And that usually is the one that most people think about. So if you have a low pH, you have a high pOH, and vice versa when you do it. To calculate the pOH, it is minus the log of the OH minus concentration. So again here, this gives you sort of a convenient way if you're maybe given the OH minus versus the H plus, because the relationship between these two is that the pH plus the pOH will equal R14. So again, conveniently, this allows you to calculate either the pH or the pOH if you're given sort of the other information. So if you want the pH, you can calculate the pOH if you're only given the OH minus concentration and then subtract 14, and vice versa. You can sort of calculate the opposite there, which is if you have the H plus given to you, get the pOH, and then you can get the pH and then subtract 14 to get the pOH. Let's see here. Other things that we talked about in terms of these sort of calculations, if you have the pH given to you, you can get the H plus concentration from it. So the H plus concentration would equal the inverse log of the minus pH. That is a 10 and a caret minus pH on your most people's calculator. And again, if you have the pOH, you can get the OH minus concentration by taking the inverse log of the minus pOH. Get that out of the way. And again, that's a 10 and a caret minus pOH, usually on most people's calculators. So as we talked about, this gives you a variety of ways, to solve some of these problems. You don't necessarily have to use H plus OH minus equals KW. You could use some of these guys to sort of short around some of these calculations to do that. Relationship, again, in terms of H plus and pH, is as the concentration of H plus increases, the pH decreases, right? And vice versa. If the H plus concentration goes down, the OH minus concentration would go up, and the pH would also go up in that case. This is why as well up here, if you're given something as sort of a strong acid or base, you could kind of do a relationship like this just to get to the H plus concentration, and that would allow you to basically calculate the pH of that solution relatively easy. Any questions on sort of that? As I keep dropping things here, grab that there. There we go. Any questions on any of that so far? All right. So a couple other important things that was in this chapter that we talked about. Obviously, we talked about the pH, the pH scale, the pOH, all those formulas, obviously, to calculate those things. We also then started talking about the idea of what happens with weak acids and even weak bases as well. So weak acids, because they are weak electrolytes, do not completely break apart. And that means that we do get weak acids, like this, where we do see those two arrows heading in both directions. And we can write an equilibrium expression for it because it is an equilibrium. And this is what gives us our Ka expression, which, just like every other K value or expression, is our products divided by our reactants. And when we talk about Ka values, as the Ka value increases, so does the strength of the weak acid. So the weak acid strength also increases because of that. And again, what that means is, because it's an equilibrium constant, if we have a high Ka value or a large Ka value, that means we mainly should have products at equilibrium. And if we mainly have products at equilibrium, that means we have a good amount of H plus being formed, which is your basic definition of your acid, and why, again, the Ka value increases, so does the weak acid strength. remember that as we talked about, even the strongest weak acid is going to be weaker than the strong acid. So, and when we're talking about sort of strong weak acid, it's in comparison to other weak acids in terms of that. Because these are weak acids, we do need to do an ice table to solve for these guys. Major difference on this ice table is not much, other than when you solve for X, you typically, that will equal your H plus concentration. And then you could go into the pH equation typically on a problem like this. So that's sort of the major slight difference there between sort of the previous chapter and this chapter in terms of concentration. Last chapter, chapter 13, we're interested usually in just sort of everybody's concentration at equilibrium. Here we most likely would be more interested in the H plus concentration to get to the pH. You would do all your same stuff. If you had a small Ka value, you can make an assumption, you could solve with the quadratic and so forth. Now, we also talked about the idea that strong acids do not have Ka values. And again, they don't have Ka values because if they are strong acids, again, they are one-way streets here. So everybody's going to the products. So nobody would be coming back to the reactant side or anything like that. Now, we also talked about, when we talked about weak acids, the idea of percent ionization. Percent ionization is basically how much of that acid breaks apart into H plus, basically how much it breaks apart into its ions. And the calculated percent ionization, as we talked about, is essentially the calculation that you do to sort of check when you make an assumption. You basically take the X value, which is the H plus value, you divide it by the initial concentration of the acid. So HA here is our initial concentration of the acid. And again, I'll give you sort of your percentage ionization. We also did somewhere we kind of used this to sort of backwards calculate the Ka value of an acid because we'd be able to figure out the X value in that ice table and kind of go backwards. We also had Kb values, right, which dealt with weak bases. And weak bases, for example, NH3 is a common weak base, ammonia, plus some water. Going to get some ammonium hydroxide. And again, this is a base. The NH3 is actually picking up the H plus. And in this case, we're going to generate OH minus. And our Kb here, just like anything else, products over reactants. And same idea, as the Kb value increases, so this is the strength of the weak acid, weak base. And it's for really the same reason. If we have a large value of K, in this case, what that means again is we have mainly products, and we should have a good amount of hydroxide being formed, which obviously would make it a stronger weak base than sort of a one that has a smaller Kb value. And these guys are pretty much solved the same way. So we do our ice table here. The difference, though, really on this ice table is when we do solve for X, X is usually equal to the hydroxide concentration, which means we first need to go to our POH and then to our pH. So, you know, that's sort of the slight difference when you sort of do these type of problems is, again, you typically end up with the hydroxide rather than directly the H plus. So there is a nice relationship between Ka and Kb. If you take the Ka value and you times it by the Kb value, that equals our Kw, which is 1 times 10 to the minus 14. And this sort of relationship here is very useful because we may have a situation where we actually do want the Ka value versus the Kb value, or the Kb value versus the Ka value, and they sort of give us the wrong piece of information, if you will. And we could use this to sort of quickly calculate the Ka value from the Kb and Kb from the Ka value. And this very much occurs with the sort of other topic that we talked about that was really big in this chapter, which was salts and the hydrolysis of salts. And remember that when we talk about salts, there are certain salts that are what are referred to as neutral salts. And really neutral salts come from group 1 on the periodic table, and 2 on the periodic table are like a strong acid. And really, again, as we talked about, those guys are really our kind of strong bases, group 1 and group 2 on the periodic table. So really something that comes from a strong acid or a strong base, its partner is going to be relatively weak. And that is the relationship between an acid and its conjugate base. Is if it is strong, this guy is going to be relatively weak. And if the acid is weak, it's going to be relatively strong. And the same thing happens with bases and its conjugate acid. If we have a strong base, its conjugate acid is going to be relatively weak. And if we have a weak base, it's going to be relatively strong. So that sort of opposite relationship really does come into play with the salts part that we talked about and the hydrolysis here. And again, anything that comes from a strong acid or a strong base, and really salts are generated from that reaction of an acid plus a base, right? It makes a salt plus water. And again here, if we take something like hydrochloric acid, which is a strong acid, plus sodium hydroxide, which is a strong base, when they come together, we will make water, and our salt here would be sodium chloride. And when we think about this sodium, it really is two things. It is a sodium ion and a chloride ion. Sodium, as we can see here from this reaction, came from sodium hydroxide, which is a strong base. And again, it's also group 1 on the periodic table, which means it's going to be relatively weak and neutral. Cl minus came from HCl, which is a strong acid, which also means it's going to be relatively weak. So without the need of any type of calculation, we would expect this guy to be neutral and have a pH of about 7 there, because it should be neutral because it is a neutral salt that's basically there. Now, when we look at something that comes, say, from a reaction of a weak acid plus a strong base. So for example, if we take acetic acid, which is a weak acid, and we react it with sodium hydroxide, OH, we again are going to get water and a salt, which would be sodium acetate. Again, when we look at the salt, it's going to basically be two things, a sodium ion and an acetate ion. And in this particular case, we could kind of use the same logic. Our sodium most likely came from sodium hydroxide, our group 1 on the periodic table. That is strong, which means the sodium is going to be relatively weak. When we look at our acetate, it came from acetic acid. Acetic acid is a weak acid, which means actually our acetate here is going to be relatively strong. And when we talk about it being relatively strong, it's not as strong as, say, a strong base or anything like that, but it's strong enough to react with water, which is why we refer to these things as like hydrolysis, because we're reacting things with water here. So what's going to happen when we generate this salt, or this salt is there? The acetate part in this particular example, which again came from a weak acid, which means when it gets to this part of the reaction, it's going to act as a conjugate base or a base. And when it reacts with water, as we talked about, it's actually going to accept the H plus just like a base would. And we will produce CH3COOH, which is acetic acid, which you always produce where the salt came from. And you will most importantly produce hydroxide here. And just by the presence of hydroxide being formed on the product side, as we talked about, we should know that this is going to be a, oops, I see bright lines everywhere, a basic solution. And more importantly, though, when we do a calculation, which would resolve in an ice table being needed to be done, this ice table would be molarity. These guys would be zeros, minus x's, plus x's, plus x's. Solve for x. And x in this case would equal the hydroxide concentration, which would get us to the POH and then to the pH. But most importantly, when we go to solve for this, that most people screw up on, right, is this part of it. Because we produced hydroxide, and in a problem where you had to do a calculation, you most likely have the Ka value for acetic acid. You actually need the Kb value here, right? And that's what this tells us as well. We do need to use the Kb value here. So most likely you would be doing this calculation with it to actually get the correct Kb value. You then can solve for, like I said, the OH minus concentration, which will then get you to your POH and then your pH. And this is what is referred to as a basic salt, again, because it will generate hydroxide, and you should obviously end with a basic pH in that particular case. Any questions on that there? And lastly, in terms of salts, we talked about really acidic salts, and that's going to happen when we really take a weak base plus a strong acid. So if we take a weak base plus a strong acid, so for example, if we took something like NH3, which is our weak base, plus some hydrochloric acid like we've seen before, again, we're going to produce NH4 plus and Cl minus, or ammonium chloride. And again, we're going to have the acid donate over to the base, the H plus in this particular case. Now, when we look at these parts of the salt, which is really ammonium chloride, we see a couple of things. First off, we see the Cl minus, like we saw previous, obviously came from HCl, not going to affect the pH, going to be neutral. But our NH4 plus did come from this weak base, which means this conjugate acid here is going to be relatively strong, which means it will go through hydrolysis. And what's going to happen again is a secondary reaction where the NH4 plus part will react with the water. And just like I labeled it here, because it came from a weak base, it's going to act as an acid when it reacts with water, which means it's going to donate its H plus over that way. And in that particular case, we will get NH3 like we talked about where it came from, and we will produce H3O plus here. And again, without even actually doing a calculation, just because we're producing H3O plus, we should know that this should be an acidic solution. And just like we would talk about with our other one, we should be using a Ka value. Remember, that's a pretty foolproof plan. If you want to determine, should I use the Ka or should I use the Kb value, is actually to look at your balanced equation. And that's why, as we talked about many times, it's really important to know how to properly write these reactions so that you can look on the product side and know, oh, I see H3O plus, or I see H plus. I should be using a Ka value if I need it. Or if I see OH minus on the product side, I should be using a Kb value in that particular case. So these are good ways, again, as we talked about, your equations can help you, your ice tables could help you as well. So we would do an ice table and it would be numbers and X's here. And as we talked about, it goes into our Ka because of that. And in this case, when we do solve for X, X is going to equal the concentration of H plus, which means we can directly go into our pH formula to calculate it. So in this sort of salt, these are referred to as being acidic salts. And again, we do produce H3O plus in that hydrolysis reaction, and thus we'll have an acidic pH. We also talked about that there's another way to produce acidic salts, and that's when you have kind of like a complex ion. So a metal in the middle has a good positive charge, something attached is a good ligand, like some waters. Right? And again, in this situation, one of the waters loses an H plus, and basically will produce H3O plus as free. And again, we would expect sort of a acidic pH with that. So again, those are sort of the three different sort of salts that we talked about: acidic, basic, and neutral salts. And again, two of them, the acidic and basic salts, do require calculations if you want to determine the pH. And if you want to determine the pH, you do need to do an ice table. And again, you could do your normal things with the ice table, but most often people screw up on, like we talked about, using the wrong K value. So again, you're using the Ka versus the Kb value. And again, you could really figure that out by looking at your equation. We also talked about how to do ice problems or pH calculations for, say, diprotic, triprotic acids. And remember, as we talked about, they do come off one at a time. So we had something like H2SO4, as we saw earlier. First thing is going to happen, H plus and HSO4 minus. HSO4 minus, H plus, and SO4 2 minus. Technically, the Ka1 here would just probably say large, and this guy would say, you know, whatever the number may be. I think we did phosphoric acid when we were in class and lecture doing it, and we had 3 K values. And again, for each of those hydrogens that come off, you'll have a K value. And the one thing that we saw, for example, let's go look at that, just that one that we actually did, which was phosphoric acid here. And remember that you could use each of these sort of individually. And what we saw when we did that calculation was that the majority, if not all of the H plus came off after that first sort of step, if you will. And remember that as you pull off that H plus, you get something like H2PO4 minus, which is now negative and a positive. So it's going to hang on to a little tighter. So it gets continuously harder and harder to remove each of those H pluses as we kind of go down that step. And again, that's what we saw when we sort of analyzed it. And the problem that we did, we were interested in like everybody's concentration, like all these guys, if I remember, which is why we had to sort of take it through each of the steps. But sort of the take-home message on that would be, as we saw there, if you had a sort of a simple question where it just really wanted you to calculate the H plus or the pH, you probably in most cases would safely be able to do it based off of the very first H plus that would come off. So again, this step here, that H plus that you got probably would be very suitable to figure out the pH from. Again, very, very, very small amounts come off from each of those steps. Yeah, so technically speaking, H2SO4 is, so the question is like why H2SO4 is maybe not equilibrium, but the HSO4 minus is. And technically speaking, we do consider H2SO4 as a strong acid. And again, it does sort of tie into what we're talking about here, that the idea is a majority, if not probably all of the H plus that would come off in H2SO4 is going to be from that first H plus that's there. And so that's why I sort of considered almost like a strong acid, that first one. But technically speaking, because it's a diprotic acid, it will still produce some of that HSO4 minus, which has the ability to produce some more H plus by losing that second H. And so that's why the second one definitely is, in comparison of this guy to this guy here, is much, much weaker and definitely sort of a weak acid and would definitely sort of follow your traditional weak acid. But because this is just specific for H2SO4 here, a diprotic acid, essentially most, if not all of the H plus is going to come off is going to be that first one. And that's why typically if you look up the value, you will find it listed in most Ka tables, but the value that they give you is almost like what I wrote right there. It will say large. And in most tables, that's essentially what it will say for H2SO4, which obviously if you're doing a calculation, it's not going to be extremely helpful to you. Because again, it's, even though technically speaking, it can fall as a weak acid, 99.9% of the time is considered a strong acid, the H2SO4, because again, almost 100% of the H plus that comes off is the amount of H plus that it would produce in that first step. And that's why, again, it's sort of considered that. And that's a little bit different than sort of here with our phosphoric acid, even though a majority of all of it is coming off here. In relationship to here, because there is 3 hydrogens involved, it's not going to as much come off. So it doesn't act as much like a strong acid as H2SO4 is. So H2SO4 considered really a strong acid, but oddly still listed in most weak acid tables for that K1 value as being large. And it's really listed there, so it's in relationship to this guy, that what it really does produce, in addition to that H plus, is a sort of, I want to say salt, but a salt part there that really will act more like a weak acid in that case. And it just has a little bit to do specifically for sulfuric acid in that case. So most of the time, if somebody did ask you about it, they would say, hey, it is considered a strong acid. Yeah, so the idea here is like what we've talked about before. We don't see Ka values or even Kb values for strong acids or strong bases, because technically speaking, kind of like I wrote it here, it's a one-way arrow and everything is heading to the product side, which means 100% of what you got going on is typically the product side. There's nobody coming back the other way. There's no reversible reaction. So like HCl, right? It's 100% going in this direction, which means in solution, you 100% have, you know, everybody on this side. This guy also is a strong acid, but the difference is because of this diprotic part of it, when it's in solution, even though you have 100% of this guy over here, you still have generated this guy, which has the ability to also lose an H plus. So again, that's how sulfuric acid sort of gets tied into like a Ka value or Ka1 value, even though they don't typically give it to you, because in comparison to a monoprotic acid, it's 100% going off to the other side, and nothing there will then produce any more H pluses. So it's because this has sort of that ability, you know, you kind of find it like that. But typically strong acid, strong bases, no Ka or Kb values. Because of that, it's a one-way street, 100% breaks apart. Other questions on that? So again, the message here in terms of the calculation part is when you do have sort of those polyprotic acids, if you simply just want the pH, again, 99% of the time, probably safe just to take the H plus concentration from that first step, that first H plus that comes off, and that probably will be correct. Remember, as we did these calculations, say we went from this ice table here to this guy, what we get for our equilibrium concentrations become our initial concentrations in all the tables that sort of follow. Then the last thing that we talked about here in chapter 14 was the idea of Lewis acids and Lewis bases. And remember that when we think about Lewis acid or Lewis bases, we're thinking about electrons and sort of like Lewis bonding and all that kind of stuff. So here when we talk about a Lewis acid, it is actually an electron pair acceptor. It accepts an electron pair. So Lewis acid is something that will accept the electron pair. A Lewis base is something that will donate an electron pair. And this is a way that we could kind of think about acid and base chemistry without having to deal with the idea of H plus being transferred, accepted, or are lost. We could do it based on electron pairs. Remember that things that have electron pairs to donate make good Lewis bases, and those are typically things that are negatively charged, because that means they have extra electrons. Are there things that are polar, that have a lone pair of electrons, like water is a good Lewis base? NH3 is also a very good sort of Lewis base. So I missed the H over there. Sure. You know, Cl minus, for example. And if you remember, we saw these Lewis bases, right, when we talked about transition metals, or more important, complex ions, the coordination compounds. These are the guys that donate in. These are the ligands that are attached in a complex ion, or Lewis bases. Things that are good Lewis acids are things that have like a positive charge, right? Positive charge implies that it has lost electrons, so it's electron deficient. So it's more apt to want to accept a pair of electrons. Also things like boron, for example, that is electron deficient just to begin with. You know, those are things that are pretty good Lewis acids as well. So again, we saw Lewis bases really pop up in a lot of other chapters, especially that transition metal one that we have a test on tomorrow. You know, they popped up a lot. And again, those are your ligands. Remember, just because something has a lone pair or non-bonding electrons, it does need to be able to sort of donate them to be a good Lewis base. And typically things with sort of separation of charge are very good in terms of donating them. Again, things with negative charges are able to do that. Things that are polar, have that separation charge overall, are able to sort of donate those things and be very good. Any questions on that there? That should wrap chapter 14. So I think that's enough torture of me talking to you today, I think. So here's the idea. Again, a reminder that we do have the exam tomorrow. And again, it is covering those two chapters in a section, really. Again, transition metal, coordination compounds, all that kind of stuff. Complex ions, including, right, crystal field theory and all that kind of stuff that we talked about. Also kinetics, all of kinetics involved. And then again, the KF, which is your complex ion sort of equilibrium is there. Again, it will be the same format. We will start it during lab time. So tomorrow we will have a lecture. We're going to continue through maybe chapter 15, maybe a little bit into 16 as well. And we'll just kind of follow through. We'll take a break. We'll take the exam tomorrow. And then on Wednesday, we'll hopefully finish up the rest of sort of this review. If you guys think this is hopefully helpful for you, I hope. If not, I don't know. So helpful, yes. Good thumbs up, thumbs down, or whatever you want to do. But hopefully this is helping you remember some of these stuff. Hopefully you do remember some of this stuff. So again, hopefully this is not something that will benefit you. It is being recorded right now. It will be posted. So with that being said, thank you for that question. I'm actually going to do something here just to make it easier for me to kind of do that part of it. What I'm going to do is we're going to take like a 15-minute break, and I'm going to stop this meeting. That way I don't have to do a whole bunch of editing, and I'll just be able to post this part of it up. And in about 15 minutes or so, if you have questions or anything like that, you could come back and I'll be happy to try to answer those questions, you know, for the rest of the time. Like I said, if you have any type of specific questions or anything I can help you with, you can chat me. If you're good by yourself today and you really don't have any questions, I'm okay for today. I'm going to assume you'll be studying for your exam that's coming up. So we'll do that for the rest of the time since we did a little bit of this. So what we're going to do now is, to return, just come through the exact same link that you did for this one. The only difference is I'm just going to end this particular meeting right now. That way I don't have to do a whole bunch of editing on it and stuff like that. And I could just upload sort of the lecture part of it here. And again, if you do have questions, definitely you should come back, obviously, and ask that. Otherwise, you're officially supposed to be studying, yes. But if you do have questions, I'll be happy to answer those. You could just chat me those questions and stuff like that, and I'll talk back to you. And that's what we'll do for the rest of the period at this point. Any questions on that? So it is, what is now, about 4:12. So why don't we break until 4:30? And at 4:30, come back through the exact same lab link that you came through here. And again, if you have questions, I'll be more than happy to answer them and stuff like that at that point, okay? Other than that, make sure you put here if you haven't done so already, and then I'll see everybody at 4:30 again. That'll give me a chance to shut this down, and then we can continue on.